Ok.
Attends.
Ok,
ça,
ok.
ça n'update pas là-bas. Attends, pourquoi? Ah. Je change ici. Attends, je vais essayer de redémarrer le truc. Ah, mais pourquoi? Là, il reste bloqué sur la première slide, en fait. Attends. Ah. Alors, attends, laisse-moi aller voir dans les écrans. Je vais essayer de dupliquer. C'est bon.
Okay, so hi everyone, and thank you, Fabian, for accepting this invitation. So Fabian is a professor at ULB in Brussels since 2016 now. He's primarily a theoretician, working with nonlinear equations, and that he applies to self-organization, pattern formation in many elegant problems. So today we'll talk about the fluid structure interaction problem, and I'll let you speak. Thank you.
So, good morning, everyone. Thank you, Arno, for the kind invitation. So in this presentation, I will talk about fluid structure interaction, and more precisely about oscillation and coalescence of slender structure. So this work has been done in collaboration with colleagues from UMOS, so physicists and also biologists, and with my student, Beatrice Hua, which is a PhD student, and Emmanuel Sieffer, which is a postdoc. So this work has been performed in the context of a project where we try to understand how some animals capture fluid to feed or to hydrate. This is why we work with biologists. And for the moment, we are interested by bees. So there are more than 20,000 species of bees, and almost half of them are characterized by a long tongue decorated with elongated papillae, as you can see on those same images. So what you see here is the central part of the tongue, which is here. So this is called glossa. And on this central part, you have this elongated papillae. And to capture nectar, bees dip their tongue 5 times per second into the liquid. So what you see here is a capillary tube with some sugar solution in it. Here is the bees. And you will see that to capture the nectar, the bees dip 5 times per second. And you can have a look at this capture process under a microscope equipped with a high-speed camera. So what you see here is the liquid, so the sugar solution. Here is the bee. And when the bee captures the nectar, so it dips the tongue inside the liquid, and you see that the papillae open. Okay. And so here in this talk, I will not tell you about the connection with the biological system. I will talk only about the physics. And here is the inspiration for the physical problems. So when the tongue is outside the liquid, actually the papillae are attached to the glossa thanks to the capillary force. And so you have coalescence of slender structure. The slender structure in this case is the papillae. And when the tongue enters the liquid, the papillae relax to their equilibrium position. And so we try to understand this kind of phenomena, and we then use some physical model to describe this. And in this talk, I will talk about relaxation of band rod in a viscous fluid in order to try to describe the relaxation of papillae. I will explain the experiment and the theory. And also I will talk about the coalescence of two slender structures, rods or lamella, when they are withdrawn from a liquid bath, but withdrawn quasi-statically. We are only at that stage for the moment. And I will talk about experiment and theory. So we'll start with the relaxation of a band rod in a viscous fluid. So the experimental setup is quite simple. You have a rod inside a liquid. One extremity of the rod is clamped, and the other extremity is free and displaced by a distance d. Okay? And then you let the system go. And you observe essentially two types of regimes. You have the underdamped regime, which happens when the stiffness of the rod is large or when the viscosity is low. So here is an example of a steel rod in water. So here this is the rod, which is bent, and you let it go, and you see that the tip of the rod oscillates and until you return to the equilibrium position. And you have another type of regime, overdamped, which happens when the stiffness of the rod is low or the viscosity is large. Here is again a steel rod, but now in glycerol. And now the rod returns to equilibrium without oscillation. So what you can do now is to measure the position of the tip of the rod as a function of time. This is what I call WE. And in this plot, you see this position of the tip of the rod rescaled by the initial displacement as a function of time. If you are in the underdamped regime, you have oscillation of the tip. This is what you see here. And we define the T, the crossing time. So this is the time at which the tip of the rod passes through the equilibrium position for the first time. So when you are in the underdamped regime, this crossing time is just related to the period of oscillation. It's 1/4 of the period of oscillation. And when you are in the overdamped regime, where you don't have any oscillation, then this crossing time is just the relaxation time. Okay. So now you can also measure this crossing time as a function of some parameter of the system. And for example, here, this is the evolution of this crossing time as a function of the length of the rod. So you see many experiments that has been performed with different type of rod, different materials, and different lengths, of course. Yes? No. No. No, no, no. No, no. And, okay. Here, what I will show also is not an exponential. And so for different, so the experiment is performed for different type of rod, different materials, different radius, different lengths, of course, and different liquid, water, glycerol, silicone. And first of all, you see that you have points all over the place. Here I show you some time evolution of the tip of the rod. So here it's underdamped, here it's overdamped, and here just to show it's critically damped, so you have only one node. And in addition, and nevertheless, you can see some scaling. So for some data, you see that the crossing time vary like the length of the rod to the square. For some other data is the length to the cube. And even for some other data is with a power 3.6. But for a given value of the crossing times, you see that you can have different regimes. So to understand what is going on, we need a theoretical model. And we did something quite simple. At least we tried. And so you have a moving rod, which is not that much deflected. So we use the dynamical linear beam equation, which is here. So this is, W is the transverse displacement of the rod. So this is the acceleration. Rho bar here is linear density. And the elastic term, you have here the bending modulus, which is written here for a cylindrical rod. So E is the Young modulus, and R is the radius of the rod. And now, normally, this equation should be coupled to a fluid equation, so Navier-Stokes or Stokes. Here, what we do is to simply add a viscous force to this, and we also take into account the fluid inertia. And now you need to choose a suitable force for that. And again, we did something very simple. We took the force, the viscous drag experienced by a rigid cylinder moving at a constant speed v, perpendicular to its symmetry axis. So here the cylinder is perpendicular to the slide. And so it's force computed from a 2D problem. It has been computed by Lamb. And the expression is the following. So the viscous force is proportional to the viscosity, quite classical. Also is here proportional to the velocity. But you have this correction, C is just a constant, and you have a logarithmic correction which involves the ratio of the velocities divided by critical velocities, characteristic velocities. And this characteristic velocities is the following one. So it's the ratio between the viscosity and the product between the liquid density and the radius of the cylinder. And actually, V over Vc is the Reynolds number of the problem. Okay. And now, if you want to use this force into this equation, you just need to replace V by the velocity of the rod. But as you see, you have a logarithmic correction. And if you want, and this is always what I want to do, if you want to do some analytical treatment, this logarithmic correction, and inside this logarithmic correction you will have a derivative of W, makes things a bit complicated. So, but nevertheless, if you rescale the force by this factor, you see that the right-hand side depends only on the ratio V over Vc. And now you can plot this rescale function as a function of V over Vc, which is essentially the Reynolds number. So this is the force, and you plot it as a function of V over Vc, and you get the orange curve here. So the dot line is actually the region where this force is no longer valid because it diverges at some point. So this has been computed at low Reynolds number. And what you can see, so this region is the region relevant for bees, but I'm not talking about this here. What you see is that in rather good approximation, this force can be approximated by power laws. In this region, it's almost linear, but not totally linear. The exponent is 11 over 10. And in this region, okay, the approximation is a bit less good, but still, in first approximation, it's also another power law with an exponent 4 over 3. So, if you accept to lose some accuracy, you gain in simplicity, and you have the expression of this, you approximate the force by a power law with an exponent sigma that depends on the typical Reynolds number of your experiment. And now you can substitute this into the equation, and you get this expression. So the viscous force is here. Notice that I have replaced the velocities by the absolute value of the velocities because when it's computed with a cylinder, the velocities is always a given sign. But when you oscillate, the sign of the velocity changes. So you put absolute value and you take into account the sign of the velocity here in front of it. Okay. And this equation now needs to be solved with boundary conditions. So you have a clamped extremity, you have a free extremity, and you have the initial condition, the initial shape of the rod when it's initially displaced, and 0 velocities. And now what you can do also is to look at some scalings from this equation. So let's first look at the underdamped regime where you have oscillation. So remember that I'm interested in the crossing time, so it's related to the period of oscillation. And when you have a damping, the damping modulates the amplitude of oscillation but does not change the period of oscillation. And so in that case, you can forget about the viscous force, and you have only a linear equation here. And if you look at the order of magnitude of each term, the order of magnitude of the transverse displacement is the initial displacement you impose, d. the characteristic value of time is just the crossing time we search for. And for the bending term, you have a fourth derivative in the x direction, so along the symmetry axis of the cylinder. So the typical value of x is the length of the rod L. And now if you sum for t, you get t proportional to L square. And if you remember, in the graph where I showed the raw data, we have some scaling like L square. Okay. And now we can look at the overdamped regime, where you don't have any oscillation. In that case, you can forget about inertia. And you have to balance the elastic term with the viscous term. The typical order of magnitude of the velocity is just the initial displacement divided by the relaxation time in that case. And now if you solve this equation, depending on the value of sigma, I show you that depending on the Reynolds number, you can have two values of sigma. For sigma equal 4/3, you get that t behave like L cube, which also correspond to what we see in the raw data. And for sigma equal 11/10, you get an exponent 40/11, which is about 3.6 as in the experiment. Okay. So now you can also, the idea now is to adimensionalize this equation to do some asymptotic analysis. And to find a suitable rescaling, we look first at the time at which, the condition at which you go from underdamped to overdamped. This happens when these two time scales are equal. So if you equalize these two quantities, you get a ratio of dimensionless parameter equal 1. And what are those dimensionless parameters? You have k here, which involve essentially all the parameters of the system except the initial displacement. And d bar is d over L, where L is essentially the radius of the rod. And so L appears as a suitable length scale to rescale the transverse motion, because d is the initial displacement in the transverse direction. And so now we rescale the equation. Along the x direction, so along the symmetry axis of the rod, we rescale by the length of the rod. For the transverse motion, we rescale with this length scale L. And for time, we rescale by tau, which is just this length scale divided by the characteristic velocities that appear in the viscous force. And now if you do this rescaling, you get, of course, a dimensionless equation that depends only on a single parameter, which is this k here. And now you can look what becomes the scaling we obtained before using this new variable. And the scaling are the following. So in the underdamped regime, which correspond to k large, as you can see here, for example, large Young modulus, etc., or large radius. So here this is underdamped, so it oscillates. You have this scaling, t over tau is proportional to k to the power minus 1/2. And when k is much smaller than 1, you can have two types of scaling depending on how small is k. You can have these two scaling. So here is just scaling. We don't have the coefficient, but we can do a bit better. We can do asymptotic analysis. So I will just give the idea. I will not go into the detail. For example, if I start with the underdamped regime, in that case, we neglect again the viscous force, and you get just a linear equation to solve. It's quite easy. You use separation of variables. Here, WE is just the position of the tip of the rod as a function of time, and G of X will give you the profile of the rod. You substitute in the equation, you get a system of 2 ODE, where sigma is the separation constant, with suitable boundary condition for the position of the tip of the rod. This is the initial displacement, 0 velocities. And for the profile, here the two first means that this extremity at x equals 0 is clamped. Here this extremity is free. This is just a linear eigenvalue problem to solve. You can solve it. You get non-trivial solution, provided that the eigenvalue satisfy this equation. And in our case, because in the initial shape of the rod there is no node, Okay. Using the first mode is enough to get a rather accurate description. So the first eigenvalue is this value. And now that you know sigma, you can easily solve this equation. This is an harmonic equation with this initial condition, and you get simply a cosinusoidal evolution with an angular frequency, which by definition is 2 pi over the period of oscillation, given by this quantity. And now you can compute the crossing time. This is just the period of oscillation divided by 4. And you recover, of course, that t is proportional to k to the minus 1/2. But now you get the coefficient. And the coefficient, because you know sigma, 0, is about 0.45. So we get this. And now you can do the same for the overdamped regime. In that case, you neglect inertia. You have this equation to solve. And in the overdamped regime, you don't have any oscillation, so the velocity does not change its sign. Here in this problem, the velocities, the sign of the velocities is negative. So I'll replace by this. And I simply remove the absolute values by considering minus the velocities. So now again, to solve this, you use separation of variable. You get two ODEs, they are non-linear. Eta is the separation, the constant separation. And now this non-linear eigenvalue problem, you can solve it numerically for the two value of sigma. And you get this value, okay? And now you can solve this non-linear equation, but this is first order, so you can do it for these two value of sigma. And you get a polynomial evolution of, it is a polynomial relaxation dynamic. So it's not exponential because the force is not linear. You would get an exponential relaxation only if you use a linear force.
So is this non-linear term coming from the loss of the...
Yeah. Yes? No, it stopped at t equal when t is equal to capital T, then you reach infinite time. That's the difference with an exponential. Okay. So of course t here I didn't say it, but it should be smaller or equal to capital T. And in the process, you get the expression of the crossing time. And again, you find back the right exponent, obviously. And here you see, because it's a nonlinear forces, you see that you get a slight dependence on the initial displacement. Quite normal if this is nonlinear. But in the experiment, this factor here are close to 1. And for this talk, I forget about it, to make it simple. And so now we have all the scalings with all the coefficients, and we have, for the overdamped regime, we have the evolution of the position of the tip of the of the rod. Sorry. And we can compare this asymptotic expression with numerical solution where we don't neglect inertia, and also with experiment. And here this is when the exponent of the viscous force is equal to 4/4, so for some value of the Reynolds number. It's a semi-log plot. So this is the evolution of the position of the tip of the rod as a function of time, rescaled by the crossing time. So the straight line here would be an exponential decay, so you see that it's quite different. And we get a rather good agreement, first of all, between the numerics and the asymptotics. So this means the asymptotic computation is okay. And also with the data. And now if you consider even smaller Reynolds number, then the exponent will be this one. And we see that, okay, we are almost, it's almost an exponential decay, but even experimentally, we can see that we deviate from an exponential. So, okay, yes. And now I can have a look at this raw data. So here I show you the crossing time as a function of the length of the rod. And now I will plot instead this crossing time rescaled by this characteristic time tau as a function of k to see if we get some order in this. And here is what we get. So we get a nice collapse, on top of which we can look at the scalings that we have computed here. Here for the underdamped, for the first overdamped regime, and for the second overdamped regime. So we get a rather good agreement. Okay. So now I show you the crossing time. I show you the time evolution of the tip of the rod for the overdamped regime. Now let's look at the underdamped regime, because for the moment we always neglected the viscous force, so we have just an undamped motion, which is here. But nevertheless, what you can do is actually, in the experiment, you have a damping of the oscillation. So you have actually two time scales. One time scale, a short time scale, is the period of oscillation. And one long time scale is the characteristic time for the decay. And when you have two time scales like this, you can use multiple scale analysis. And I will not enter into the detail. So if you don't take into account the viscous force, you have this expression. And these are the data for steel rod. Here it's in silicone, I believe, and here in glycerol, according to the color. If I don't take into account any damping, I get this and not it. And now if you do a multiple scale analysis, you can get this correction, where at the same time you get the relaxation time, the characteristic relaxation time here. And now if you compare with the data, you get a rather nice description of the motion. Okay, so that's what I wanted to tell you about this problem of oscillation. And now I will talk about capillary coalescence. So the experiments are very simple. We have two vertical and parallel rod or lamella. As you can see here, it's rod, here it's lamella. Partially immersed in the liquid bath. And they will be quasi-statically withdrawn from the liquid bath. You see that when the structure are immersed in the bath, you have two menisci. Because the structures are identical, the menisci are the same, and in that case, it leads to an attractive shear force at the air-liquid interface. At the beginning of the experiment, the dry length here of the structure is quite short, so the effective stiffness of the rod is large, and this capillary force, this shear force, is not strong enough to significantly deform the structure. But now, when you withdraw the structure, you increase the dry length, so you decrease the effective stiffness, and at some point, here this is what you get for rod, at some point you go into contact. And then you can plunge back the structure, and you see that they do not separate immediately. You will see here also for lamella. You see at some point, they actually snap to contact, and then they do not separate immediately. So, experiments have been performed with rods, two types of materials, glass or PET, with this value of the Young modulus, radius, and density. Has been performed also, the experiment has been performed with lamella, PET lamella, with different thickness, and we consider also different widths just to see that the width was not playing a role. And for the liquid, we use silicone oil with these values for the viscosity, density, and surface tension. We also change the viscosity because this is quasi-static. It does not play a role. And now what you can do experimentally is to measure the distance between the two structures at the air-liquid interface, that we call 2 delta, as a function of the dry length. So at the beginning here, the two structures are clamped at a given distance that we call d, and the distance at the air-liquid interface is delta, or 2 delta if you want. So now you measure delta as a function of the dry length. When the dry length is small, the structures are barely deflected, and so the distance here is almost equal to the distance between the clamp part. And now you increase the dry length, as you can see here, And this distance between the two structures decreases until you reach a critical value of the dry length where they snap to contact. And when they are in contact, if you decrease again the dry length, they stay in contact until you reach a second critical dry length, and they go back to the previous bench. So you have here a subcritical bifurcation with an hysteresis loop and the coexistence of two stable states. So to describe this, we did a very simple model. So here is the schematic of the system. Because of the symmetry, we model only half of the system. So D is the distance here between the origin and the clamp part. Delta is the distance between the origin and the extremity of the dry length of the structure. L is the dry length, and here you have the capillary force. So because the ratio between D over L is small in the experiment, there are small deflections, so we use a linear beam equation. And it turns out that we need also to take into account the tension. And I will come to the tension in a moment. So in this term, B is the bending modulus. Here it's written for cylindrical rod, here for lamella. And for the tension, you have two contributions. One comes from the capillary force itself, but it's not the dominant one. Actually, in the experiment, especially for lamella, this is the weight of the structure. So it's surprising. At the beginning, the first model I did was without tension, but it plays a role. So in the expression of the tension here, P is the perimeter of the structure, because we play both with rod and lamella. And here S is the area of the cross-section of the structure, L is the length. And here we do an approximation. It's not mandatory. We consider this is to keep everything simple, and it's enough to describe the experiment. We consider that all the weight is located at the air-liquid interface here at the bottom. Normally the weight varies with the position, okay? But if you do that, you will find a airy function, and it's a bit more complicated, but it's just technically more complicated. So here, finally, this tension is just the weight of the structure. And for the boundary condition, you have here it's clamped at x equals 0, and the other extremity is free with a shear force F. And so now you have a linear equation with those boundary conditions, so it's not complicated to solve. Let me forget for a moment this boundary condition. If you solve it with these three boundary conditions, you get this solution, where alpha is a rescale tension. And of course, because I use only three boundary conditions, you still have one integration constant, A. And we wrote the solution like this because A is a simple interpretation. If I look at the value of this deflection, so W is the deflection, at the extremity, so at the air-liquid interface, you just get 1 minus A. So 1A is a dimensionless deflection parameter. If A is equal to 0, you get straight to structure. If A is positive, you have a deflected structure. And finally, A will be fixed thanks to the last boundary condition that we have to use. So to summarize, we have this solution, we have this boundary condition to apply, and we have this relation between the dimensionless deflection parameter and the distance between the two structures at the air-liquid interface. Now, if I substitute W into this expression, I get this. Okay. And now you see that you have the product A times D, and actually A times D, from this definition, is just D minus delta. If you look D minus delta, what it is, it's just the displacement of the free hand of the structure at the air-liquid interface. And so what you see, this last equation we need to solve in order to completely solve the problem can be written like this. It's like an elastic force where with an effective spring constant K in red here times the displacement of the free hand of the structure should be balanced by the capillary force, which depend also on the position. And so now you need to know, to proceed, the capillary force. And here we do an approximation. We consider, because this is known, we consider the interaction between two straight structures. because here the structure are deflected, but not much deflected. So when they are deflected, of course, this can be perturb the menisci and change the force. And here we simply consider the capillary force between two straight structures. And this is known. This is the force for two rods, which is written here. So you see that the length scale that appears here is the radius of the rod. So this is two identical rods. And delta is the distance between the two rods. And you see that when the distance is large compared to the radius, this force varies like 1 over the distance between the rods. And a similar expression is known for lamella, where this time the characteristic length scale is the capillary length. And now the force varies like 1 over the distance to the square. And now once you have this force, you can replace here. And you get this type of equation. So I remember that at this stage we need to find A. So here we have a function of A, and also over as a function of d over r. So d is the distance between the clamp part and r, the radius of the rod. Should be equal to this quantity where lambda is actually a rescale dry length. Okay. It's not an easy trivial expression because in alpha you have also L. So this depends also on L. But this can be viewed as a rescale dry length. And for lamella, if you substitute this into this equation, you get something similar. The function here that depends on A is a bit different, but it should also be equal to lambda over the characteristic length scale of the force, the capillary length. And so now we need to solve these two equations with this expression of the rescale dry length. So here is the expression of the rescale dry length, and we need to solve these two equations. And so we can proceed graphically to understand what is going on, to see if this can explain the snapping transition. So what you have here is a function of A and also on D should be equal to this. So let me first look at rods. For lamella, I will not do it, it's similar. Let me plot first this function H as a function of A. It has this shape here. So it has a maximum value. And now this should be equal to a constant. It does not depend on A here. So let's proceed like in the experiment. You start with a low value of the dry length. So a low value of lambda, for example here. And you see that the solution of this equation is just the intersection between the green line and the blue curve. So you have, a priori, two solutions. But now if you look at the total energy of the system as a function of A, you see that this one corresponds to a minimum and this one to a maximum. So this one is stable, and this one is unstable. So the intersection here gives you the evolution of A as a function of lambda. So this is actually the bifurcation diagram. So now, as in the experiment, I increase the dry length. So I increase lambda. I will reach this critical point, where actually the two extrema of the energy will merge. And finally, if I consider a too large value of the dry length, I do not have solution, but in the energy, beside the two extrema, where the derivative vanish, you have also another local minimum, which corresponds to the contact between the two rods. And so what happens is that when you reach this critical value of the rescale dry length, you don't have any minimum of the energy when you are larger, and you go from here to this local minimum. And so you go from this value of A, which is the deflection parameter, to contact, and so you have the snapping. And so now to find the critical value of the dry length and also the critical value of the displacement, you just need to compute the position and the value of the maximum of this function. And this is a simple function. And if you do this for rods, you get this expression. These are very simple. And if you do this for lamella, the function is even simpler. You get this. So you see that here the critical deflection for rods is 1/2. This means that they will deflect by 1/2 of their initial distance before to snap. And for lamella, they will deflect only by 1/3 of this distance before to snap. So they deflect less, lamella. And now you can, so this means that here, if the rescale dry length is smaller than this critical value, and if you start from small value of the dry length, you are in open state, and as soon as you are larger than this critical value, you get into contact. And so the phase diagram actually is spanned by two parameters, the imposed distance between the structure and this rescale dry length. And so now we can compare two experiments. So in the experiment, you can measure the largest dry length before you have snapping. This is what you do. Once you have this critical value, you can compute this rescale dry length as a function of essentially the distance between the imposed distance between the structures, so the distance between the clamp part. And you get this data. And if you compare with this relation, which is very simple, almost a power law, you get this agreement between theory and experiment. So in a given experiment, it's a vertical line. You start here, it's open. You increase the dry length, you go there, and at some point you get snapping, and then you're into contact. Okay. And you can do also the same for lamella. These are the same data, but for lamella. And you get also a good agreement with this simple power. So, okay, I'm done. And so just a short summary. So for the relaxation of rods, so I show you experiments which show that you have two main regimes, underdamped, where you have oscillation, overdamped, where you simply relax without oscillation to the equilibrium position. And we have measured the position of the tip of the rod as a function of time, and also what I call the crossing time. Theory, we use the dynamical beam equation with viscous force obtained from a rigid cylinder. We showed that the viscous force can be approximated by two power law, just to simplify the computation and get analytical result, and we obtain good agreement with experiment. And for the capillary coalescence, in the experiment we look at direction through through two menisci when the structure are withdrawn from a liquid bath. And we showed experimentally that there is a discontinuous transition to contact, so snapping, when you reach a critical value of the dry length, and they detach when you reach another critical value, which is smaller than the previous one, so you have an hysteresis. And for the theory, it's simply a linear beam equation with a shear capillary force at the interface. From the theory, you can compute bifurcation and phase diagram, which agree well with the data. Okay, thank you for your attention.
Thank you, Fabian, for this impressive talk. Thank you. Is there any questions in the room?
Thank you. I was wondering if you can describe the hysteresis with your theory or with other.
No. Alors, this is a good question. So here with the theory, we can compute only L plus, but we cannot compute this one, and the reason is this is because of the approximation we did when we consider the force between straight structure. In this case, if the structure are straight, when they are in contact, then the contact zone extends over all the structure over all the structure. And so we overestimate the capillary force. And actually, if I go back, yes, here. Actually, we found that the contact is always a local minimum of the energy. And this is for any values of the dry length, which is not possible. So within this theory, actually, the structure never detach. So we cannot compute L minus.
You have an idea. So you
But
want
I think L minus is exactly what Benoit, José, and Areski computed in your. This is you have an expression, this famous Nature paper, where you have the expression of the dry length, and I think that L minus. We didn't check this, but I think it's known in the literature. It's the same. It should be. It should be the same.
Thank you. Another question for Sébastien?
I think I remember Raymond Goldstein from Cambridge, UK, had a theory for the vibration of a beam in a low Reynolds number fluid. How does your equation compare with his equations?
I don't know. I don't know this equation. What I know is that most of the time, when it's about the relaxation of rods in a fluid, most people use finally the relaxation time, which is come from a linear force most of the time. And so I never saw this before, but we were surprised actually at the beginning. We look into the literature, thinking that it was done. It's a very simple experiment, and we didn't find anything. And the paper is now published, so the referee didn't complain. And so, up to my knowledge, it was not done before, and it's surprising. Yes, I agree.
And I have another question on the second system. How can you maximize the volume of the water that you are withdrawing from the bath?
This is a good question, and this is something that we have to work on, but we didn't hear. So actually we started with that question to look, because actually in the case of biology we are interested to understand how much you can capture, and so we started with that, and but then we saw this snapping, etc., transition when we were doing the experiment, and said, well, let's first try to understand this. And so we have first some preliminary results, but cannot talk about it for the moment. But it's planned. Yeah. So yes. The to-do list here, there are many. But the obvious one are you still keep two rods, because with lamella it's a bit complicated, and you had a finite withdrawal velocity. It changed a lot. The capillary force is really much stronger. We see it in the experiment. The challenge now is to get a good description of this capillary force, which is not. And this is one thing. And the other thing is to, but it's also because those experiments looks very simple. Well, for the oscillating rod, it's okay, but for the coalescence experiment, it looks very simple, but it's much more complicated than it looks like, because the structure to be parallel. At some point they can be quite long. That's the first thing. And also, each experiment needs to be done several times, not only for statistics, because at the beginning you start with a too long length of the structure. And so when you remove, you have the part that is immersed inside that start to interact. Okay, in itself is also a problem that could be studied, but we didn't want to study that. So you first do the experiment to see where is the critical length, and then you have to cut and to do again, etc., to avoid this interaction of the immersed parts of the so, and so we could consider dynamics, but we could also consider three rods, for example, but quasi-statically. And then, but Emmanuel and Adrien, with three rods, they are not really motivated. They say it's a nightmare, because now you need to control three distance, and it starts to become very complicated. So now, for the moment, we work with two, and we work on the dynamics.
For me, just one quick question with the capillary coalescence. Just because I'm curious, like even if you go quasi-static, this experiment, if you do your full experiment, then it so you go up, it snaps, and then it desnaps with some hysteresis. If you do that again, it's the same LC plus, or you have no memory of the nothing that stays on the.
No, no, not significant actually. Not significant actually. Yeah.
Okay. We have time for one question.
Yeah.
In the first part, the multiple scale analysis at the end, it's what is it? It's hard. It's easy.
Ah,
To, you know,
it's yeah, it's many pages of computations. Yes, yes, yes. It's
different one.
yeah, especially here because you deal with a nonlinear force, and so there are some. It's very technical, so I didn't want to spend. I could do just one talk, at least 20 minutes to explain all the details of the calculation. Yeah. But it's a powerful technique. Actually, the idea of this is that you consider that you have two times when the times need to be quite separated. Here it's the period of oscillation and the characteristic time for the decay of the amplitude, and you consider these two times as independent variable. And so even if you have an ODE, you transform this into a PDE. So it looks that you complicate the problem, but okay, at some point you can, and it's very powerful. Most of the time, you need to be in a regime where the, here in our case, the viscous force should be small enough, so it's perturbative. No, it's a technique to solve the ODE you have. I don't know. Yeah. Ouais. But you don't go through the energy, so maybe it's equivalent to what you say. I don't know. And I never look that way into the problem. Yeah. Yeah.
Okay, thank you again, Fabian,
Thank you.
for this very nice presentation.